This discussion we're going to get into how do we tune terms and amplifier in terms of its bias current, as well as briefly look at the linearization again of a simple OTA amplifier. And in fact, what we would be looking at is a simple amplifier like the structure over here, which is going to be an OTA element, going to have an output current. That current is going to be related to the difference of the two input voltages. And of course, practically, it's going to be integrated on a capacitor. So this whole structure is going to give me a first-order filter. But I'm going to start by a capacitor with this element in the derivative, and then it's going to relate to this nice tangent function if I'm dealing with a subthreshold current. Great. The bias current's outside of it, but then I have this sort of tangent of this nonlinear function. Well, within a certain region, this is going to be considered linear. That's going to be typically when, V in minus V out is roughly around 2 UT. Now, for a good observer, you'll notice a kappa is missing there for a good subthreshold design. My apologies. There should be a kappa sitting right there. You linearize it, and we do get to keep the kappa in the next stage. Is going to be the kappa I bias over 2 UT times the difference of the inputs. So basically, it looks like a transconductance, which basically says the difference of the inputs on the one side gives me some current times a term is called the transconductance, which we'll call GM. And so as a result, I can also then say my time constant will be capacitance divided by GM. Okay, this is good, and so now I've got you can see where this could become a first-order filter. Okay, we probably have seen this in some other context. Now, here's the interesting question. How much can I program things? Well, let's assume I've got a device that can run subthreshold over a range of bias currents, and this is certainly a possible thing you can do. And so, what could happen? Well, imagine if I put a picoamp current, and some people will ask, well, wait a minute, can you really make an amplifier with a picoamp of current, bias current? And the answer is yes, actually very routinely. The second question is, well, isn't it just too noisy to work? And the answer is no, that's not true. You're going to get the same total KT over C noise over the bandwidth that you're working with. So no, it actually works out fairly well. Now you have to be careful with the rest of your infrastructure, but otherwise it works fairly well. And I can go a picoamp, nanoamp into a microamp, and you'll notice that the transconductance just scales linearly all the way through, all the way into these elements. And you think, okay, well, what's the implication of that? The implication is that my cutoff frequency will move from 6 Hz to 6 MHz by simply just tuning a knob. Now, I will typically above a microamp start getting well above threshold, so things will start to slow down as I go up a little bit further. And I might imagine my transconductance is not going to get nearly as high as I go up, but I will still get some improvements, and I will utilize this where I can. And so I can certainly get additional frequency. But here's the interesting part. I can sort of set this voltage, and therefore set this whole range of frequencies over 6, 7, 8 orders of magnitude with the same structure. This is pretty phenomenal. You could imagine this is a huge opportunity. By the way, in case you're wondering how effective this is in terms of filters, these will typically be the most power efficient and sort of low power approach of any filter you're going to be. The trade-off, of course, technically is going to be questions of linear range, and that's where you usually will have to have some challenge and some trade-off in this particular topology, but a very powerful topology for building filters. Now, the question, so the cool thing is this is electronically tunable, and that is a gigantic advantage, particularly if you have a good capability of setting that voltage, particularly in a non-volatile way. That's a great approach. Unfortunately, the disadvantage, depending on what you're building, is I also need a method to set this frequency or this voltage or this tuning. That could be a huge stress point depending on who and what and what kind of technology you're building with. If you happen to have, for example, a good non-volatile programming technique, this becomes really nice. If you're having to set this in a very traditional way by making sure you've got matching of resistances and capacitances and trying to set the standard voltage sources, you might have to be very careful about building a good tuning structure. But the opportunities here look huge, and so I think the opportunities clearly outweigh any of the other issues you would run into, but you have to be aware of them, otherwise you might not get a design that actually is effective that you're looking for.